Back this a bit. Thinking about long-term missions to the moon, it's a massive goal, right?
Absolutely huge.
But here's something you might not think about right away. What do we actually do with all the trash generated up there?
Yeah, that's a surprisingly big hurdle. You can't just leave it lying around, obviously.
And constantly shipping it back to Earth for long missions, that's just
Well, it's not going to work, is it?
not sustainable at all. The cost, the logistics, no. So the real question becomes, how do you manage waste totally off-world, self-sufficiently?
Exactly. Which leads us perfectly into what we're digging into today, the NASA Lunar Recycle Challenge.
Ah, yes, the $3 million competition.
Right. It's all about finding really innovative ways to handle waste on the moon. And what I find clever is the structure, 2 tracks.
The prototype build and the digital twin.
Yep. One for building actual hardware, the other for creating these super detailed virtual models.
That dual approach makes a lot of sense. You get the hands-on, practical side with the prototype.
But the digital twin lets you, simulate and test ideas really rapidly under all sorts of conditions without building everything first. It's smart for such a complex problem.
Now, some listeners might be thinking, okay, moon garbage. Why is that relevant to me?
Fair question.
But it's not just about space housekeeping. This challenge is seriously pushing the boundaries of recycling tech. The moon's environment is so harsh, the solutions have to be incredibly efficient and robust.
And those kinds of solutions, well, they could have major benefits back here on Earth. Think about remote communities or disaster zones.
Totally. Reducing solid waste, boosting sustainability. The potential terrestrial spin-offs are pretty exciting.
Lightweight, efficient systems, those are needed in many places, not just the moon.
So our mission for this deep dive, first, we'll explore the Lunar Recycle Challenge itself, the goals, the setup, the core issues.
Got it.
And then we get into something really interesting, a brainstorming session between 2 AIs, Grok and ChatGPT, tackling these very problems.
Oh, that should be fascinating. Seeing how AI approaches this. How do you even start thinking about waste in such an alien environment?
Exactly. And just so everyone knows, our sources for this are NASA's info on the challenge itself, plus transcripts from that AI brainstorming session. Lots of interesting stuff there.
Okay, so let's start with the basics. What makes lunar waste management so uniquely difficult? What's the core problem Lunar Recycle is trying to solve?
Well, fundamentally, you need a system that's incredibly efficient. Uses minimal power, minimal resources.
Sure.
It also has to be super lightweight. Every single kilogram launched costs a fortune, right?
Absolutely critical.
Yeah.
Mass is always a driving factor in space missions.
And it needs to have a really low impact on the moon itself. You can't just set up a lunar landfill.
Definitely not. Preservation is key.
And like we said, hauling trash back home, just not feasible long term.
The costs are just prohibitive. You need closed-loop systems, handle it there, ideally turn it into something useful, or at least drastically reduce the volume.
And then you add the lunar environment itself. It's brutal.
Yeah, talk about constraints.
Massive temperature swings, right? Boiling hot during the day, incredibly cold at night. We're talking hundreds of degrees Celsius difference.
Minus 173 C to plus 127 C, roughly. Huge swings.
Then there's the vacuum. That affects how materials behave, how processes work.
And don't forget the radiation. High levels. Any equipment needs serious shielding or hardening.
So any recycling system has to survive all that. Extreme temps, vacuum, radiation, it dictates everything from materials to mechanics.
It really does. Robustness is non-negotiable.
Okay, so when we talk about waste on the moon, what are we actually dealing with? Grok's analysis broke it down nicely.
The different streams.
First up, packaging. All the plastics, metals, composites wrapped around equipment and supplies.
Yeah, that'll be a big one, especially early on. Everything arrives packed. Food, instruments, tools.
Then food waste. Organic leftovers from meals. Human waste, obviously.
Yeah.
Solids and liquids.
A necessary reality.
And then mission byproducts. Kind of a catch-all, right? Worn out tools, used filters, other operational stuff.
Makes sense. Things just wear out or get used up.
And Grok even estimated some of the smaller bits, like hygiene products, maybe 0.05 kilos per person per day.
Okay.
Medical waste, hopefully low, around 0.01 kilos. Even textiles, like old clothes, maybe 0.005 kilos daily.
It doesn't sound like much individually, but over weeks, months, with multiple crew members.
It adds up fast. Which brings us back to the Lunar Recycle Challenge details. We mentioned the 2 tracks, prototype build and digital twin.
Right. Prototype is physical hardware.
Building actual recycling machines designed for solid waste. getting your hands dirty, basically.
Demonstrating it can actually work.
And the digital twin track? That's all virtual, right? Building this incredibly detailed computer model of a whole recycling system.
Exactly. Simulating everything, collection, processing, turning waste into new stuff. You can test countless designs and scenarios without building physical prototypes each time.
Like a super advanced simulation game for your lunar recycling plant.
Pretty much. It allows for massive optimization. Test under different lunar conditions, simulate making end products, all in the computer.
And the deadline for registration is March 31st, 2025. The whole competition runs for about 6 months after that.
That's a tight time frame.
It is. And apparently that time frame influenced Grok's thinking a bit. It leaned towards the digital twin track, maybe because you can iterate and simulate faster within 6 months.
That makes sense. Physical prototyping takes time and resources. Digital twins offer agility, especially under deadline pressure.
So if you were entering, how would NASA judge your solution? What are the key things they're looking for?
It's all about practicality for the moon. Energy efficiency is huge. How much power per kilogram of waste processed?
Right, power is precious.
Mass, obviously. Total system weight. Got to be light.
Uh-huh.
Environmental impact on the moon, operational feasibility. Can astronauts actually use it safely and easily?
Makes sense.
And, of course, the core function. Recycling capability. What percentage of waste actually gets converted into something useful?
So basically, low power, low weight, safe, easy to use, and actually does the job well. Turns trash into treasure, or at least less trash.
That's the essence of it. And the exciting part we touched on earlier, the spin-offs.
Right, the Earth applications.
Yeah, the tech developed for the moon, super efficient, robust, lightweight systems could be adapted for remote areas here, disaster relief, places where normal waste systems are down or non-existent.
It really shows how pushing the limits in space can spark breakthroughs back home. It's a fantastic potential double benefit.
Absolutely. Solving extreme problems often leads to widely applicable solutions.
Okay, great overview of the challenge. Now let's dive into that AI brainstorming session. Grok and ChatGPT tackling lunar waste. How did they start?
Well, Grok's first move was pretty logical. It basically said, let's split the waste into two main piles, organic and solid.
Okay, that seems sensible. Food scraps and human waste versus plastics and metals.
Exactly, because they have very different properties, and you'd likely treat them differently. Allows for tailored recycling strategies.
So, starting with the organic stuff, food, human waste. What were Grok's ideas there?
Grok leaned towards biological recycling, specifically anaerobic digestion.
Like composting, but without oxygen.
Precisely. Using microorganisms to break down that organic matter in a sealed, oxygen-free environment. Think of it as a high-tech composter using specific microbes.
Similar to biogas generators we have on Earth.
Very similar principle, and the byproducts are really valuable. First, you get biogas, mostly methane.
Cool. For power on the moon base.
Exactly, a potential energy source. And second, you get digestate. That's the leftover solid and liquid material.
And what can you do with that?
Well, it's nutrient-rich. Could be processed into compost, or even more excitingly for the moon, liquid fertilizer.
Ah, fertilizer. For growing food. That connects directly to long-term plans for lunar agriculture, doesn't it?
It absolutely does. Grok specifically mentioned using it for hydroponics, growing plants and nutrient solutions without soil. A key technology for potential lunar farms. Talk about closing the loop.
That's brilliant. Waste becomes food. But surely doing this on the moon has unique problems. Microbes and microgravity.
Yeah, Grok flagged that. Microgravity's effect on bacterial activity isn't fully understood. That's a research area.
Okay.
And you'd obviously need specialized contained bioreactors. Can't just have open tanks. Needs careful environmental control within the habitat. Safety and efficiency are paramount.
Right. Everything contained, controlled. Okay, so that's organic. What about the solid waste stream, plastics, metals, etc.?
For solids, Grok focused mainly on mechanical recycling. The core idea was shredding plastic waste.
Okay, break it down physically.
Yep, and then turning that shredded plastic into filament to filament for 3D printing.
The 3D printing angle. Making spare parts, tools, right there on the moon from recycled plastic. That seems incredibly useful.
It's a huge potential win. Reduces the need to ship every single spare part from Earth. Saves mass, saves cost, increases self-sufficiency.
Makes total sense. But what about metals? Recycling metal usually takes a lot of heat, right? Lots of energy.
Exactly. Grok acknowledged that. Melting metals is energy intensive, and energy is a premium resource on the moon. Plus, you have composite materials, mixtures of stuff, which are even harder to recycle.
So, melting down old wrenches with solar power might be tricky, at least initially. What did Grok suggest instead for metals?
Lower energy options were proposed. Maybe just compressing metal waste to reduce its volume for storage,
Okay, compact it down.
or possibly finding temporary uses for it, like maybe incorporating it into radiation shielding structures. Basically, manage it without high energy melting for now.
Gotcha. Now, the conversation apparently shifted towards pyrolysis. That sounds technical. What is it?
Pyrolysis is basically heating materials to very high temperatures, but crucially without oxygen present.
So, not burning it, more like baking it intensely in a vacuum.
That's a good analogy. It causes thermal decomposition. The material breaks down into different components. What you get depends on the waste type and the temperature.
And why is that useful for lunar waste?
The potential is that it could handle a mix of wastes, maybe organics, maybe some plastics, and the outputs can be useful too.
Like what?
Things like syngas, that's a mix of hydrogen and carbon monoxide, which can be used as fuel,
More fuel.
bio-oil,
Yeah.
another potential fuel or chemical feedstock, and a solid carbon-rich material, maybe useful for building materials or again, shielding.
Interesting. So, turning mixed waste into fuel and solid carbon products.
Potentially, yes. And this links back to the biogas idea too.
How so?
Well, the suggestion was if the anaerobic digestion is producing biogas, methane, maybe you could use that biogas as the energy source to power the pyrolysis unit.
Whoa, wait. Use the gas from processing organic waste to power the system that processes other waste.
Exactly. Creating a more integrated, efficient system. Waste powering waste management. It's a very appealing concept for a closed loop.
That's really elegant thinking, but pyrolysis still needs high temperatures, right? Where does that energy come from if not biogas?
Another innovative idea was using solar concentrator mirrors.
Like focusing sunlight.
Precisely. Lightweight mirrors focusing sunlight to create a small spot of incredibly high temperature. It was proposed as a potentially lightweight, energy-efficient alternative to plasma torches or microwave heaters for reaching those pyrolysis temperatures, harnessing the sun directly.
Using the moon's abundant sunlight during the day. Clever. What about other ideas for metals, beyond just compressing them?
Yeah, there were a couple more. One was about design foresight.
How do you mean?
Proactively choosing materials for mission hardware that are easier to recycle later, like using lightweight metals with lower melting points, maybe certain aluminum alloys.
So if stuff is made of easier to melt metal, then recycling it later with solar power becomes more feasible, designing for recycling from the start.
Exactly. Smart design upfront makes downstream processing easier.
Makes sense. And there was one more kind of low-tech idea for metal.
Right. Using human power. Imagine astronauts using a manually operated piston press to compress metal waste.
Like a big trash compactor, but astronaut-powered.
Sort of. And to make it easier, maybe you could preheat the metal slightly using solar energy just to soften it a bit, reducing the force needed.
Get a workout, recycle some metal.
Could be. Every little bit helps reduce volume.
Okay, so that covers a lot of Grok's ideas. Now, ChatGPT apparently focused heavily on CO2 management. Why is CO2 such a big deal?
It's critical for life support. Astronauts exhale CO2 about a kilogram per person per day. In a sealed habitat, that builds up fast and becomes toxic.
So you absolutely have to remove it.
You have to remove it, and ideally you want to recycle it, turn it back into something useful rather than just scrubbing it and storing the waste.
And ChatGPT looked at some pretty advanced ways to do that, using pyrolysis or plasma reactors, leveraging the moon's vacuum.
Yes, exactly. The vacuum is actually helpful for these kinds of high-energy reactions that don't rely on catalysts. ChatGPT outlined three main chemical pathways for CO2 conversion.
Okay, let's break those down. What's the first one?
First is splitting CO2 into carbon monoxide, CO, and oxygen, O2. CO2 becomes CO plus 12, O2.
And what's the use of those?
Well, oxygen is obviously vital for breathing air replenishment,
Crucial.
and carbon monoxide. That could be a precursor for making other fuels, or even used as a reducing agent to help extract metals like iron from the lunar soil, the regolith.
Wow, okay. So processing regolith using a byproduct of breathing.
Potentially. And ChatGPT noted plasma torches are reasonably efficient at this conversion, maybe 20–40%. So breathe out CO2, zap it, get oxygen back, and a useful chemical.
That's pretty neat. What's the second reaction?
The second is the Sabatier reaction. This combines CO2 with hydrogen, H2, to produce methane, CH4, and water, H2O. CO2 plus 4H2 becomes CH4 plus 2H2O.
Methane is rocket fuel, right? And water is, well, Water, essential.
Exactly. Methane could fuel ascent vehicles or landers. Water is critical for life support, drinking, hygiene, and you can also split it via electrolysis to get hydrogen and oxygen back again.
Closing loops all over the place. But where does the hydrogen come from?
That's the key dependency. You'd need a source, maybe from water ice deposits found in lunar craters, or potentially extracted from the regolith itself, though that's complex.
But if you can get hydrogen, this reaction is powerful. Is it used already?
Yes, a version of it is used on the International Space Station to generate water, though it typically uses catalysts, not plasma.
Got it. So breathe out CO2, add some lunar hydrogen, get rocket fuel and water. Amazing. What was the third option?
The third was high temperature pyrolysis of CO2 directly into solid carbon, C, and oxygen, O2. CO2 becomes C plus O2, O2.
Solid carbon, like soot.
Sort of, yeah. Carbon black. This could potentially be used in composite materials to add strength or radiation shielding properties, or maybe even as a feedstock for 3D printing carbon-based structures. And again, you get oxygen.
More oxygen, but this one sounds energy hungry.
It is. ChatGPT highlighted that it requires very high temperatures, so the energy cost is significant.
Okay, 3 different ways to tackle CO2, all producing really valuable stuff. O2, CO, methane, water, solid carbon.
Exactly. And ChatGPT pointed out the moon's specific advantages for these processes.
Like the vacuum.
Yeah, the vacuum helps. Abundant solar energy, potentially nuclear power later on. The reactors could be made compact and scalable. And as we mentioned, the potential for in situ hydrogen.
It really paints a picture of using the lunar environment itself to enable sustainability. Did ChatGPT mention any real-world examples or related research?
It did. It referenced ESA's MOXIE experiment on Mars.
Ah, the oxygen generator on the Perseverance rover.
Right. MOXIE successfully converted Martian CO2 into oxygen using solid oxide electrolysis. The proof of concept for this kind of atmospheric processing.
So the basic tech exists and works off Earth.
And NASA apparently looked into a microwave dissociation of CO2 back in the 90s for space habitats. So there's a history here.
Okay, so bringing this all together, Grok also gave more detailed estimates for the daily waste amounts per person. Can we recap those numbers?
Sure. Grok put food and human waste as the biggest chunk, around 2 kilograms per person per day. That includes food scraps, feces, and urine.
Mostly water weight, I guess.
A lot of it, yes. Which is why biological recycling to get biogas and that liquid fertilizer seems like such a good fit for this stream. High potential there.
Right. What about packaging?
Estimated at about 0.3 kilograms per day. The focus there, Grok suggested, should be reused first. Then, mechanical recycling plastics to 3D printer filament. Metals may be melted eventually.
Makes sense. And the CO2 we just talked about?
Around 1.00 kilogram per person per day. Huge potential for conversion into O2, CO, carbon, or methane water if you have hydrogen.
And the other category? Tools, hygiene, medical.
That was smaller, estimated around 0.092 kilograms daily total. Includes worn tools, hygiene items, medical waste, textiles. Grok thought the recycling potential here might be lower initially.
So prioritize repair, repurposing, maybe just compaction for storage, or perhaps pyrolysis for some of the trickier mixed materials in that category.
That seems to be the thinking. Focus on the big three. First. Organics, packaging, and CO2. They represent the bulk of the waste stream.
Okay, so for you listening, the key takeaways here are pretty significant, aren't they? This isn't just about trash collection.
Not at all. It's fundamental to enabling long-term human presence off-world. We saw some really cool ideas discussed.
Like the closed-loop life support, potential turning waste into fertilizer, air, water.
And using solar power for metal recycling, or 3D printing tools from plastic trash. These are the kinds of innovations NASA's challenge is aiming for.
And the bigger picture connection is crucial too. Solving these incredibly tough problems for the moon
forces us to develop technologies and approaches that could revolutionize recycling and sustainability right here on Earth.
Learning to live with limited resources and zero waste in space could teach us invaluable lessons for managing our own planet better.
It's all about that circular economy mindset. Waste isn't an endpoint, it's a resource. The extreme constraints of space just force us to get really, really good at it.
Absolutely. So here's a final thought to leave you with. We talked about the potential for growing food on the moon eventually.
Right, in situ food production.
How would that shift producing more food locally instead of shipping it all change the waste profile? Would you have less packaging waste, but maybe more agricultural waste? How would that impact the design of recycle systems?
That's a great question. Great question. It really pushes you to think about how these lunar habitats might evolve into more complex, truly self-sustaining ecosystems over time.
Definitely food for thought. The Lunar Recycle Challenge is clearly just the beginning of figuring all this out. It's going to be fascinating to watch how these technologies develop. Okay,